Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This course is on introductory transport phenomena based on the book by Welty, Rohrer, and Foster. We are looking in Chapter 1, Introduction to Momentum Transfer, and we're going to be discussing properties at a point. The first property that we want to define is density. Now, density is mass per unit volume, and if you look at a small elemental volume of size delta V, its mass would be delta M. And density at the point is going to be what happens when we take the limit of this as delta V approaches a small, tiny size dV. That's the volume of our point. And based on our discussion of a continuum, we want our point to be just large enough that we have moved into the continuum, and it's at an average of that microscopic range. That is to say, we're going to be stretching the mathematical definition of a point instead of being infinitesimal to being just a teeny bit larger than that so that we still have the continuum. Density and most of the fluid properties that we'll define are a function of the state or the compressibility of the function of the fluid. And a lot of times we're going to be able to treat these as constant, and we can look up tabulated values of these. In our book, Table 1.1 has an assortment of common accepted density values. The second of these properties that we want to consider is stress. Now, stress is a measure of how surface forces are applied to a small area. So these are on a surface, and that's going to be really critical. Any force that we have can be broken up using vector notation into a normal component that is perpendicular to this surface and one that lies on the surface or tangentially. We're going to designate those delta Fn for the normal one and delta Fs for the tangential one, or the shear force. The normal stress is going to be this normal force divided by the size of my little elemental area, and we will take that down to a small size where, again, we're still in the continuum view of our fluid, but microscopic. That's going to be the sigma sub II, okay? The shear stress is going to take that shear component, the one that lies on the surface, and divide that by the unit area. And in our book, they designate it tau sub ij. Now, the notation is a little complex. So for the normal surfaces, we are again talking about the things that are going perpendicular to the surface. And so if you think about these surfaces, and the X and Y are designated here, oriented at the center of this small area, the first subscript denotes the face on which the stress acts, and the second is the direction on that face. And so for the normal stress, they're acting in the X direction, and that face is at a position X, right? So we go to positive X or negative X. And then we can use arrows to designate positiveness or negativeness. For the shear stress, we want to use the first subscript again is the face on which the stress acts. The second is the direction on that face. Now, I find it very helpful here to think of like the X in this case as being the left-right and Y is top-bottom. So the tau that we look at here, the tau xy, is going to be, okay, the face on which the stress acts is the first X, so it's acting on the right face, okay, and it's the direction on that face, and it's the Y, so the upward direction. So on the left face, upward direction is tau sub xy. Tau sub yx, on the other hand, is acting on the top face and in the right direction. Negatives of those would be going in the opposite direction or opposite face. The final property that we want to discuss at this point is pressure. And pressure is force per unit area, and it is the normal force per unit area. Okay? And the key thing to know about this is that it is the same in all directions at a point. So whether you look to the left or right or up or down, it will be the same at every location or in every direction. So we're going to look at this a little more closely in another video, but for now we can just treat this as a fact. We'll demonstrate that fact in another video. So that concludes our view of properties at a point. Next, we're going to be looking at that proof of the fact that pressure is the same in all directions, and then we'll look at what happens as you move from point to point. Thank you very much for your time. If you have any questions, please feel free to contact me.